that brings me to Paul Vallejo. Now, I'm really looking forward to this. How many opportunities do we have here in Australia to hear from an aerospace engineer who spent over 8 years at NASA? He's also spent time in Texas universities teaching political sociology and macro and microeconomics. And I have been told on good authority that he is a real guru on nuclear technology. Please welcome him to the stage, Paul Vallejo.
All right, I'm here to talk to you about nuclear power, the good kind. But first we have to talk about the corrupting influence of narratives. Narrative science and narrative news are the opposite of what they claim to be. We all know that there's more than one side to every story, but the idea of a narrative is to make you think there's only one side. Narrative science is a corruption of the scientific method. Don't try to read this slide. We'll go into this shortly. In narrative science, it only cites studies that work towards a predetermined conclusion. And they try to confuse scientific consensus with data and launch ad hominem attacks at people who disagree. Real science doesn't argue from conclusions. Real science is humble. Real science invites falsification. A scientist, a true scientist, who embodied that philosophy was Albert Einstein, who said, "No amount of experimentation can ever prove me right. A single good experiment can prove me wrong." That is the philosophy you want in a real scientist. Narrative news is similar in that you start from a pre-existing conclusion, usually echoing the talking points of powerful interests. They will find experts to support that conclusion and ignore events that go against the narrative they want to show. So we'll just go through a few of these real quick, and then we're going to get to nuclear power and those narratives as well. We have an expert here who will talk more about the Great Barrier Reef in 2017. These headlines were all over the place. I was in Mexico last month, and diving in Cozumel, people thought the Great Barrier Reef was gone, because this narrative news was all over. This was not covered in the news, that the reef, in many ways, is at a multi-decade high. We'll hear more about that later. The Arctic sea ice, same thing, narrative news. In 2013, the Arctic sea ice was supposed to vanish. 2014, Al Gore said that the polar ice cap would disappear. End of the Arctic, ocean will be ice-free by 2015. In 2013, they said, in 2 years, there will be a methane catastrophe as the melting sea ice will release methane into the atmosphere, accelerating the greenhouse effect, and we're all going to cook. What actually happened? 2012 was the low of Arctic sea ice. In 2021, there's been no change in Arctic sea ice for the last 10 years, but you will not find news articles saying, you know what, don't worry about it. It's all, things have stabilized. That's not the way narrative news works. They move on to whatever recent event will maintain the narrative. You won't find articles that talk about it. You'll find maybe some small articles that talk about it, but if you use Google, you certainly won't find it. Search engines are also narrative search engines. If you haven't realized that Google is curated search engines, that's something that should be looked at as well. Now let's talk about green energy and the narrative around green energy. There's a narrative and a counter-narrative. Both sides have merit in terms of the arguments. We need to know the best side of both sides of the argument. There's also a nuclear narrative and a nuclear counter-narrative. A little bit about me. Most of this got covered in the introduction, but what I will say is I've lived here in Australia for 11 years. I've been a citizen for about 5. One of the things that people wonder is, like, they ask me what brought me to Australia. And I've traveled to dozens of countries, and what I like to say, and it's true, is that of all the countries I've been to, Australia was the first place I went to that felt like home. I wanted to raise my kids here. and I'm very grateful to be here. It's a wonderful place and a wonderful people, and I'm very grateful. Oh, one other thing that I'll say real quick. My first major at uni was nuclear engineering. I diversified that into aerospace engineering. I have not calculated neutron absorption cross-sections in decades. I'm rusty, but since nuclear energy has been banned for a couple of decades, you're not really swimming in nuclear engineers, so you get what you can get. Chemical and nuclear energy are fundamentally different. Every form of energy you see around you comes from chemical energy, the rearranging of electron shells, the breaking of bonds between molecules, whether it's burning petrol or photosynthesis or using batteries, it's all chemical. No is changed in chemical energy release. In nuclear energy, whether it comes from fusion, which powers the sun, combining hydrogen atoms into helium atoms, or fission, the splitting of atoms, whether it's uranium or thorium or natural nuclear decay, the energy released from nuclear processes is far and away of a different class than chemical energy. And this is really important because energy density is going to be a major factor in why nuclear can be such an important opportunity. If you look at all the chemical sources on the bottom, they can release between 10 and 100 megajoules per kilogram, whereas nuclear can release in the millions. Order of magnitudes different. Energy density is a huge factor for nuclear, and it's an opportunity. And yes, it has risks, but those risks can be managed with modern designs. What you want to know for your power sources is, does it have a reliable supply, and is it safe? First, we're going to talk about domestic supplies. Uranium and thorium reserves. Now, most people understand that uranium is the source of nuclear power plants. Thorium can be used as well. The reason why thorium power hasn't been used is that the first use of nuclear reactors was not to make power, it was to make weapons. And for that, uranium was better to be used. So that's why we have a long history of using uranium for power, but thorium can be used as well. Australia is in the top 3 in reserves for both uranium and thorium. I don't know about you, but in an uncertain world, things that my life counts on to be domestic, if at all possible. Magnets for wind turbine blades needs rare earth magnets, and China holds most of that supply. Batteries require lithium, which we do have in abundance in Australia, and cobalt. And in cobalt, 60% of the world's supply comes from the Congo, often mined in what they call artisanal mining. It's not a very pretty process. I think Joe Rogan did an episode on cobalt mining fairly recently, which is a good one to look up. Next, baseload power. What's baseload power and why is that important? Wind and solar are intermittent. Our modern economy is not. Wind and solar, it's the luck of the draw, what you get on that day. Wind's too fast, you have to shut down the turbines. Wind's too slow, the turbines don't spin. Whoops. And demand has to be met every day at all times. Otherwise, you're going to have a blackout. So nuclear can provide baseload power, whereas wind and solar cannot. If you are going to use a carbon-free source, and I don't think you need to in the short term, maybe eventually, what you want is stable baseload power. The economy has a certain amount of power that it draws at all times. And yes, there are peaks and valleys, but nuclear can provide you consistent power. Whereas wind and solar is a bit of the luck of the draw. And the question is, when wind and solar aren't in your favor on that particular day, who's going to party like it's 1699? Who's going to go without freezers or refrigerators or hospitals that have power? Candlelight dinners sound romantic, but it's not something that is going to work for our modern economy. Next, safety. Modern designs can be designed to be walk-away safe. But our narrative and what we kind of know from the TV is we're judging nuclear by old designs. Fukushima, Chernobyl, 3 Mile Island, those are all good shows on Netflix. But they were designed in the 1960s, built in the 1970s, And this was the state of art of our telephones at that time. This was the state of art of our personal computers. Okay, we need to judge apples to apples, both sides of every argument. What were examples of commercial power generating solar and wind in the 1970s? Well, you're looking at it. There was none. We have to judge modern designs by modern designs. Advanced reactors, what they call Generation 4, can consume more waste than they produce, and they can be designed to be walk-away safe. What does walk-away safe mean? It means in the old reactors, you had to have active cooling. If the water pumps failed, the electricity to the reactor failed, the reactor core might overheat, and you could have an uncontrolled meltdown. And that's what happened in Chernobyl, for instance, and Fukushima. A modern reactor can be designed so that if, for whatever reason, the cooling system fails, what you have here on the bottom, there's a freeze plug, and the freeze plug is kept cold by the electricity to the plant. The electricity to the plant goes out, the fuel dumps into an energy dump tank, the safety operators can go to lunch and then go camping, come back, and nothing catastrophic will have happened. It's a design issue, and it can be designed to be walk-away safe. Nuclear is already the safest way to make energy. This is one of those things. We have to count our costs on the mining side, on the production side, and then also on the disposal side. An adult in the room has to count all aspects, not just look at the shiny panel that goes on the roof and not where did that silica sand come from and how is it going to be disposed. You have to count all things.